Hello and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the step response of an RL circuit. And essentially in this video, what we want to do is we want to derive an equation for I of t and V of t given two situations or two cases. The first case being when this switch is open and essentially L is at an initial condition or is uncharged. And the second case being when this switch is closed, right, after a time t is greater than 0, and we want to derive an equation for V of t and I of t through this inductor L and see what that equation looks like. So similar to my past videos, I would like to define what the step response of a circuit is. And essentially, the step response of a circuit is its behavior when excitation is the step function, which may be a voltage or a current source. And essentially, I'm going to describe a step function by using something called the unit step function, where essentially it's 0 from t is equals to negative infinity to t is equals to 0. And then it shoots up, and it's called the unit step function because it saturates at 1 all the way until t goes to infinity. And the x-axis here is my time. So then the goal of this video is to find the step response of the RL circuit. In order to do this, we need to first consider a case number 1 where t is less than or equals to 0. And what I'm going to write here for notation purposes is a note that says that I'm going to say I of s of t is going to equals to just I of s. I of t, which is the current through my inductor, is going to be equals to just I, and V of t, or the voltage across my inductor, VL of t, I'm just going to write as V for the remainder of the video. And what we want to note is that I for t less than or equals to 0 is essentially just I of 0 minus, or just I naught, or the initial condition. And since current cannot change instantaneously through an inductor, again, I've talked about this in what is an inductive video, and I posted a link in the top right-hand side corner of this video. We know then that my I at 0 minus will then just be my I at 0 plus, or again, we just call this I naught. So this is my first conclusion for from case number 1, and it's basically my initial condition. All right, so the next thing we want to focus on is case number 2, or when t is greater than 0. And essentially what I'm going to do is I'm going to write a nodal analysis at this node here, call this Vx. And I'm going to say that the currents leaving have to equate to 0. So the currents leaving this node have to equate to 0. And again, I've done a video on nodal analysis, so please feel free to check that out. So essentially what I'm going to say is that on this current here is opposing Is of t. So it's going to be minus Is plus this current here is going to be Vx over R plus this current here is going to be my current flowing through my inductor, or just I, which is all equals to 0. I can then rewrite this and say then that minus Is plus 1 over R, Vx is the same as Vt, or the voltage to my inductor. And we know that the voltage to the inductor is L times the change in current over dt plus I, which is equals to 0. If I go ahead and multiply my entire equation by R over L, I then get that this term just becomes di over dt. This I term here becomes plus I R times L, and I'm going to equate this term to the right-hand side. So it's plus Is times R over L. And again, just for clarification, I in this situation is I of t, and Is in this case is Is of t. So let's not forget that. So then we want to note something about this equation and say that this is a first order linear ordinary differential equation. And essentially, this is the equation that we want to solve for. So then let's keep going on this side here. And I'm going to say then that di over dt is equated to this minus I minus is over L times R. And again, I hope that makes sense. I just move this to this side of the equation. I'm going to go ahead and multiply both sides by dt over I minus is. So then what I do get is the following. I get di over I minus is is equated to minus R over L times dt. If I then go ahead and take the integral of both sides of this from IO to I, or the I initial to some I of t, and then in this case I get 0 to t. When I take the integral of this, I get ln I minus is. Again, my parameters are going to be IO to I, and this is equals to minus R over L times t, and then this becomes from 0 to t. If I keep on going, I distribute my I into this formula and here. So then this becomes ln I minus is minus ln IO minus is is equated to minus R over L times t plus 0. So what I want to do is notice that these two ln are being subtracted from one another. So I can rewrite this as ln I minus is over IO minus is equated to minus R over L times t. And what we can do is take the exponential on both sides to get rid of my ln. And essentially what I'm left with is I minus is over IO minus is is equated to e to the minus R over L t, which I can rewrite as e to the minus t over tau, where tau is equals to L over R, and this is what's called my time constant. All right, it's a very, very important term. So then let's go ahead, and what we want to do is solve for this I, right? I of t, that was the goal. So then we can multiply IO minus is on both sides. So then we're left with I minus is is equated to IO minus is e to the minus R over L t. So then I, just to be clear and explicit, which is equals to I of t, is equated to is plus IO minus is e to the minus t over tau. And again, this is for t greater than 0. So this is the answer to my second case. So then now let's go ahead and rewrite this in a more clear manner. So therefore, to write this clearly, I'm going to say then that, let me name this one, I of t is equated to this IO, again for t less than or equal to 0, and then is plus IO minus is e to the minus t over tau for t greater than 0. And I'm going to call this what's called the complete response, or the total response. So then the second way to write this, I of t is going to be this IO, or my initial condition, for t less than or equals to 0, and then I to the infinity plus IO minus I to the infinity times e to the minus t over tau for t greater than 0. And this is called the general complete response. And just so we know, you can amend current into all these names. So for example, complete current response, total current response, and general complete current response. So I hope that makes sense. And the reason why this is called the general complete response, or why we care about it, is because we refer to this as what's called the FIFE equation. So FIFE, which stands for final, initial, final, and exponential. So that's very, very important. Again, you will use this equation many, many times, and it's good to memorize it as the FIFE equation, because then you can solve a lot of the examples in the circuits. So then now for the last one, which is the step response, we want to consider that the inductor is uncharged initially. So for example, IO is equated to 0. So then we can say then that I of t is basically 0 for t less than or equals to 0. We can say then that it's the final current, I infinity, plus 0 minus I of infinity times e to the minus t over tau for t greater than 0. So what we can do then is now say that this here, if we want to simplify it, becomes I of infinity times 1 minus e to the negative t over tau for t greater than 0. And essentially what we have here is the step response of I of t, and that is because from t is equals to negative infinity all the way to t is equals to 0, we get this 0. And then we know that as t goes to infinity, my current saturates at I of infinity. So it's going to look something like this. And so this function in this graph becomes my complete current step response of the RL circuit when the inductor is initially uncharged. So I hope this makes sense. If you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. So now let's go ahead and dive into the voltage across the inductor. So from previous videos, we know that the voltage across an inductance is L times the change in current over dt, which we can rewrite as L d over dt times IO for t less than or equals to 0. And then for the second case, it's going to be my final value I infinity plus IO minus I infinity times e to the minus t over tau for t greater than 0. So then now V then becomes the derivative of IO is just 0 for t less than or equals to 0. So then now L times the derivative of this function becomes something like this: 0 plus IO minus I infinity times negative L over tau e to the minus t over tau for t greater than 0. And what I'm going to do is I'm going to say that tau is equated to L over R. So then that means that this L cancels out with this L, and then this R comes to the top. And then note that if I distribute this negative, this becomes a plus, but then this becomes a plus and this becomes a minus. So then I can rewrite this entire thing as the following. This becomes R times I of infinity minus I of 0 times e to the minus t over tau for t greater than 0. So then let me go ahead and move this up here. And so then this becomes what's known as my general complete voltage response of an RL circuit. And the last case we want to consider is for I0 is equals to 0, which is basically when the inductor is initially uncharged. And we can say then that V of t is equated to 0 for t less than or equals to 0. And then if this is 0, this becomes R times I of infinity times e to the minus t over tau for t greater than 0. And essentially my step response, right, which is V of t as a function of t, is basically going to be 0 from t is equals to negative infinity all the way to t is equals to 0. And then it's going to shoot up, right, to this R times I of infinity, right? Because if I put in 0 here, this just becomes 1. And so since it's e to a negative value, it's going to decay exponentially back towards 0 like this. And that's going to be my step response of this RL circuit. Okay, if you found the video helpful, please give it a thumbs up and please share the video. If you have any concerns, please leave them down in the comment sections below and I'll be sure to get back to you. If you like what the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.